In the spring of 1964, on a low rise in Holmdel, New Jersey, two radio astronomers tilt a giant metal horn toward a patch of empty sky. Arno Penzias, 31, and Robert Wilson, 27, expect silence or nearly so. Instead, their receiver delivers a faint, steady hiss, a hum riding beneath every measurement they attempt. It does not fade, it does not spike. It simply persists, a background whisper that refuses to leave. They check the frequency, 4.080 megahertz, a wavelength of about 7 centimeters. At this band, the sky should be nearly dark, disturbed only by known catalog sources. This signal matches nothing in the catalog. Their first assumption is the obvious one. Instruments fail. Amplifiers overheat. Cables leak. Somewhere in their electronics, they reason, a fault is generating spurious warmth. So they begin the slow discipline of elimination, expecting to find the culprit within days. But the hiss defies their expectations in a way that unsettles them. They swing the antenna toward the horizon, then toward the zenith, then toward the quiet regions between stars. The noise stays exactly the same. They wait for morning, then noon, then midnight. The noise stays exactly the same. They wait through spring into summer, tracking whether the signal follows the sun, the seasons, the rotation of the earth. It follows nothing. It is isotropic, arriving with equal strength from every direction at once, as if the entire sky were glowing faintly and uniformly at a temperature just a few degrees above absolute zero. This is not how interference behaves. A ground source would fade when they pointed upward. A city transmitter would come from one bearing. A solar contribution would rise and fall with the day. This hum obeys none of those rules. It saturates the cosmos evenly, indifferent to where they aim their instrument. Penzias and Wilson are meticulous men, trained to distrust anomalies. They do not yet suspect they are hearing anything profound. They suspect only that something is wrong with the machine they have inherited, a strange and enormous machine built for another purpose entirely. To understand their confusion, we must first understand the horn itself. The instrument that captured the hiss was never designed to study the cosmos. It was built for commerce. In 1959, Bell Telephone Laboratories erected the Holmdel horn antenna, a 20-foot aluminum funnel weighing several tons, mounted so it could pivot to sweep the sky. Its purpose was practical, to catch the faint microwave signals bounced off Echo, an early reflective balloon satellite, and later off Telstar, launched in 1962. These were the first fragile experiments in relaying communications across continents by bouncing radio waves through space. The horn's peculiar shape served a precise function by funneling incoming waves down a narrowing throat to a receiver at its apex. The design rejected stray radiation from the ground and the surroundings, admitting only what came from the direction it faced. It was, for its era, one of the quietest and most sensitive microwave collectors on Earth, engineered to hear whispers from thousands of miles above. Once the satellite work wound down, the horn sat available, a superb instrument idling between assignments. Arno Penzias and Robert Wilson recognized its value at once. Both were radio astronomers who wanted to measure faint natural radio emissions, and here was a device tuned to detect exactly the sort of dim, cold signals ordinary telescopes drowned out. They inherited the antenna, hoping to map the quiet radio glow of our own Milky Way, the low hum of interstellar gas at high galactic latitudes. To do this properly, they needed to know their instrument's own background with extraordinary precision. Every antenna adds a little warmth of its own, a self-noise measured in degrees of temperature. Their plan demanded they subtract that internal contribution cleanly, leaving only the sky. So they built a reference source cooled with liquid helium to just above absolute zero, a cold standard against which to compare the heavens. They intended to account for every fraction of a degree, to strip their measurement down to certainty. That was the ambition, a clean, quiet baseline, and then the galaxy. But the baseline would not come clean. A stubborn excess of warmth clung to every reading, and no amount of care would remove it. So they turned, methodically, to hunt the fault. If the noise was real, it had a source, and Penzias and Wilson set out to find it with the patience of engineers. Their method was elimination. Name every possible cause, test it, rule it out. Begin with the obvious external suspects. Nearby New York City throbbed with radio and television broadcasts. Could urban transmissions be leaking into their receiver? They checked the bearing toward Manhattan and found the noise no stronger from that direction than any other. Radar installations dotted the region, powerful and pulsing, but their hiss was smooth and constant, nothing like the sharp signature of radar. They considered the sun the most powerful radio source in the sky and watched the signal as the sun rose and set. It did not follow. They considered nuclear weapons tests. A high-altitude detonation in 1962 had seeded the upper atmosphere with charged particles that could, in principle, generate radio noise. But that contamination should have decayed month by month. Their signal decayed not at all. Then they turned inward, suspecting their own equipment. Amplifiers generate thermal noise when warm, so they scrutinized every component. They rebuilt connections. They examined joints in the antenna's aluminum skin, where rivets and seams might radiate faint warmth of their own. They taped over gaps with aluminum tape to seal any leakage. The hiss remained. They calculated and recalculated the contribution of the atmosphere itself, the thin warmth of oxygen and water vapor overhead. They subtracted the known emission from the ground, spilling into the horn's edges. They accounted for the loss in every wall and throat of the instrument. When they added every explainable source together and subtracted it from their measurement, an excess stubbornly survived, a residual warmth of roughly 3 degrees above absolute zero that no accounting could dissolve. This was the maddening part. Each test tightened the mystery rather than solving it. Every candidate they investigated turned out innocent. The noise was not New York, not radar, not the sun, not their electronics, not the atmosphere. It came from everywhere, equally, always. And yet there remained one source they had not examined, something living inside the antenna itself, leaving a physical trace on the metal throat. Inside the great throat of the horn, where it narrowed toward the receiver, Penzias and Wilson discovered they were not alone. A pair of pigeons had taken up residence in the sheltered aluminum funnel, nesting in the very space where the instrument gathered its faintest signals, and the birds had left something behind. Coating the interior surfaces was a white residue, the accumulated droppings of their occupancy. Penzias, ever precise and diplomatic, described it in the language of physics rather than biology. He called it a white dielectric substance, a material that might absorb and re-radiate microwave energy, adding warmth to their readings. Here, at last, seemed a mundane explanation. Any material clinging to the antenna's inner walls could generate thermal noise, especially if it warmed under the sky. Perhaps the mystery had feathers. They acted accordingly. First, they addressed the pigeons themselves. The birds were captured and shipped away to another Bell Labs site, though, pigeons being pigeons, they reportedly found their way back, and firmer measures eventually followed. Then the astronomers turned to the residue. They climbed into the horn and cleaned the aluminum surfaces, scrubbing away the dielectric substance, restoring the metal to its intended reflective bareness. With the antenna cleaned, the birds evicted, and the interior scoured, they ran their measurements again. Surely now the excess warmth would drop. Surely the pigeons had been the answer all along. It was not. The hiss remained exactly as loud as before. The reading held at that same stubborn value, roughly 3 degrees above absolute zero, unmoved by all their labor. The cleaning had removed only a negligible fraction, if anything at all. This was the moment the ordinary explanations ran out. They had eliminated the city, the sun, the radar, the atmosphere, the electronics, and now even the pigeons and their residue. Nothing terrestrial, nothing local, nothing living accounted for the sound. What confronted them was not a defect they could scrub away, but a genuine feature of the sky itself, a warmth woven into every direction they could point. And that warmth had a number, a temperature that refused to die, uniform across the entire heavens. The number they kept arriving at was small, precise, and inexplicable. The excess signal corresponded to a warmth of about 3.5 degrees above absolute zero, a temperature so cold it lies just a whisper above the theoretical floor, where all motion ceases, minus 273 degrees Celsius. In the language of their field, they had measured an antenna temperature, a way of expressing radio intensity as the heat of an equivalent glowing body. And that glow was everywhere. What made the measurement so unnerving was not its size, but its uniformity. When they aimed the horn at one region of sky, they read the same value. When they swung it to another, the same. Toward the plane of the galaxy, away from it, high and low, morning and midnight, the reading held constant. The signal was isotropic to the limits of their instrument, identical in every direction. Nothing in the known universe behaved this way. Consider the alternatives they had already dismissed. The sun's radio emission rises and falls with its position and its storms. The Milky Way glows unevenly, brightest along its crowded plane, dimmer toward its poles. Heat from the ground spills into an antenna only from below. A single star, a nebula, a distant galaxy, each occupies one patch of sky. But this warmth came from all patches equally, as though the entire celestial sphere were a body held at the same faint temperature. And it never changed. Day after day, season after season, the value persisted without variation, without decay, without any dependence on where Earth sat in its orbit, or how the sky wheeled overhead. It was as permanent and featureless as the sky is deep. Penzias and Wilson faced a fact they could not interpret. They had a clean, repeatable, carefully calibrated measurement of a real phenomenon, and no framework to explain it. They were radio engineers who had cornered a cosmological truth without knowing its name. The answer, it turned out, was not in their laboratory, nor in any textbook they possessed. It was being written at that very moment by a rival team roughly 30 miles to the southwest, in Princeton, where physicists were building a detector to hunt for precisely this signal. "30 miles southwest of Holmdel, in the physics buildings of Princeton University, a very different kind of search was underway. Robert Dicke, a formidable experimentalist, had grown convinced that the universe began in an unimaginably hot, dense state. If that were true, he reasoned, the fireball of creation should have left a residue, a faint bath of radiation cooled by billions of years of cosmic expansion, still lingering across the whole sky. Working with him were Jim Peebles, who worked the theory, and Peter Roll and David Wilkinson, who were building a small horn antenna on the Princeton roof to hunt for it. Peebles calculated the leftover heat should register at roughly 10 degrees above absolute zero, later refined downward. They were, in effect, constructing the exact detector Penzias and Wilson had already accidentally become. Neither team knew the other existed. Then chance intervened. Penzias, still puzzled by his stubborn noise, mentioned it in a phone conversation with a radio astronomer named Bernard Burke. Burke had heard, through a colleague, about a preprint of Peebles' work predicting cosmic background radiation. He suggested Penzias call Princeton. Penzias picked up the telephone and reached Robert Dicke. As Penzias described the persistent hiss, the uniform temperature of about 3.5 degrees, its refusal to vanish from any direction, Dicke listened in silence. Then he covered the receiver, turned to his team gathered in the room, and spoke a sentence that would become legend. "Boys, we've been scooped." The signal Dicke had spent months preparing to chase had already been captured, 40 miles away, by two men who had spent a year trying to make it go away. Dicke drove to Holmdel with his group. They examined the antenna, the measurements, the meticulous elimination of every earthly source. Everything fit. What Penzias and Wilson had called an annoying technical problem was the precise fingerprint the Princeton theorists had predicted from the birth of the cosmos. The two stories, one accidental and one deliberate, had converged on a single, staggering conclusion. But no one had yet spoken aloud, in plain words, what this whisper truly was, or how impossibly ancient the light pouring into that horn had become. To understand the signal, wind the clock back nearly 14 billion years. In its first moments, the universe was a scorching, opaque plasma, a fog of protons, electrons, and light so dense that no ray could travel far before scattering. Photons ricocheted endlessly, trapped in a glowing prison. For 380,000 years, the cosmos remained this blinding haze, expanding and cooling with every passing millennium. Then came a threshold. As temperatures fell to about 3,000 degrees, electrons finally slowed enough to bind with protons, forming the first neutral hydrogen atoms. In an instant, cosmically speaking, the fog lifted. The universe became transparent. Light that had been trapped was suddenly free to stream across space, and it has been traveling ever since. This moment is called recombination, and the light released is the oldest light there is. But over billions of years, space itself stretched. As the universe expanded, it dragged those ancient light waves with it, stretching their wavelengths longer and longer. What began as a fierce visible glow, thousands of degrees hot, was pulled down through infrared and into the microwave band, its temperature dropping to just under 3 degrees above absolute zero. This is exactly what Penzias and Wilson detected. The static in the Holmdel horn was not interference from radar or the galaxy or pigeon residue. It was the surviving radiance of the infant cosmos, redshifted across the entire history of time, falling into a New Jersey antenna. It came from every direction because it fills all of space, a relic sea of photons that once touched the whole young universe. Every square centimeter of that horn was being struck by particles of light older than the Earth, older than the sun, older than any star. The hiss they had chased and cursed was the universe itself, still faintly speaking, a background murmur left over from the moment matter and light parted ways. They had not discovered a flaw in their equipment. They had discovered the echo of creation. Now this whisper needed to be written down, published, and set against the reigning theory of the cosmos, a theory it was about to shatter. In 1965, the discovery reached print, not in one grand announcement, but in two brief papers, side by side in the Astrophysical Journal Letters. The first, by Penzias and Wilson, was a model of restraint. Titled A Measurement of Excess Antenna Temperature at 4080 megacycles per second, it ran barely 2 pages. It described, in careful and cautious language, the excess temperature of about 3.5 degrees, its uniformity across the sky, its stubborn refusal to disappear. Nowhere did the authors claim to have found the birth cry of the universe. They simply reported what they measured. The second paper, by Dick, Peebles, Roll, and Wilkinson, supplied the meaning. Titled, Cosmic Blackbody Radiation, it explained that this faint glow was precisely the relic radiation expected from a hot, dense, early universe. 2 papers, one measuring, one interpreting. Together they told the story neither could tell alone. The consequences were seismic. For decades, cosmology had been split between 2 rival visions. The Big Bang model held that the universe had a beginning, a hot, dense origin from which everything expanded. The steady-state model, championed by Fred Hoyle and others, insisted the universe had always existed, unchanging on the largest scale, with new matter created continuously to fill the gaps. The steady-state cosmos had no need for a fiery birth, and therefore no reason to leave behind any afterglow. The cosmic microwave background was the one thing steady-state could not explain. If the universe had no beginning, there should be no leftover heat, no uniform sea of ancient microwaves bathing all of space. Yet there it was, exactly as the Big Bang predicted. A whisper of 3 degrees was enough to bring down an entire worldview. The evidence was quiet, but it was everywhere, and it was undeniable. Slowly, then decisively, the scientific community shifted. The Big Bang became not merely a hypothesis, but the foundation of modern cosmology. All from a hiss 2 men had tried to eliminate. Recognition would follow, and with it, instruments far more powerful than a single horn. Machines built to read the faint light in extraordinary detail, and to trace it back to the very first structures of the cosmos. In 1978, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Arno Penzias and Robert Wilson for their discovery of the cosmic microwave background radiation. The 2 men who had spent a year hunting for a fault, cleaning pigeon droppings from a horn, and doubting their own instruments, now stood among the highest honored in science. Robert Dick, whose team had predicted the signal, was not included, a decision many still debate. But the prize confirmed what the whisper had already proven. The universe had a beginning, and its afterglow had been caught. Yet the horn at Holmdel had only opened the door. To truly read the ancient light, scientists needed to escape the interference of Earth's atmosphere. In 1989, NASA launched the COBE satellite, the Cosmic Background Explorer. From orbit, COBE measured the radiation with breathtaking precision, confirming its temperature at 2.725 degrees above absolute zero, and showing its spectrum matched a perfect blackbody, exactly as a hot early universe demanded. Then COBE found something more: tiny fluctuations, variations of 100,000th of a degree, ripples in the primordial glow. These were the seeds of everything, the first faint clumps that would grow into galaxies, clusters, and stars. In 2001, NASA's WMAP mapped these fluctuations in sharper detail, pinning the age of the universe at 13.8 billion years. In 2009, the European Space Agency's Planck satellite refined the picture further, producing an exquisite full-sky map of the cosmic microwave background, a portrait of the universe as it was 380,000 years after its birth. What began as an annoying hum in New Jersey had become the most detailed baby photograph ever taken. Every mission, every measurement, traces back to that persistent static 2 astronomers could not explain. They had reached for the quiet glow of our galaxy and instead touched the edge of time itself. The oldest light in existence, stretched across 14 billion years, still falls upon us in every direction, at every moment, carrying the memory of creation. In that faint, patient signal lies the simplest and most profound truth science has ever recovered. The universe left us its first light.